In this video, we will be describing the Van Hoff factor, which is essentially a scaling factor applied to molecules that break up into ions when they dissolve in the solvent. Because the colligative properties that we have been working with depend on the total concentration of the solute, not the identity of the solute, compounds that break apart or dissociate instead of dissolve tend to have a larger impact. If we look at two examples, sugar dissolved in water versus table salt dissolved in water. When sugar dissolves in water, it goes from the solid form to the aqueous form. The molecule itself stays together. However, table salt, sodium chloride, when it breaks apart, it breaks up into sodium ions and chloride ions. What this means is instead of having just one molecule dissolved in solution, you actually have two different solute molecules. You have a sodium ion and a chloride ion. So essentially your solute concentration doubled versus what you would think it would be just from looking at the initial sodium chloride that you put into the solution. The term that we use for compounds that break apart into solution to form ions are electrolytes. The Van Hoff factor is a way of accounting for this splitting of your molecule into smaller ions. However, because the ions themselves do attract to each other, in solution, what you'll have is some of the ions associated with each other or next to each other, which in essence decreases their effective concentration to a lower value. What I mean by this is, for example, sodium chloride, some of your sodium ions and some of your chloride ions, instead of being freely independent, will be close to each other, and instead of acting as two separate solute molecules, will instead act as one. So what you would expect from having the molecule break apart into its two ions, that increase in concentration will actually not be as high as you would predict. So essentially, when sodium chloride breaks up into two ions, the scaling factor that needs to be applied is not quite 2. Some of the sodium ions and some of the chloride ions will stay close together in solution, reducing the effect. That is what the Van Hoff factor is meant to account for. We use the symbol I to indicate the Van Hoff factor, and this is the moles of particles that are actually in solution divided by the moles of formula units dissolved. The formula units, in this case for the sodium chloride, this would be your sodium chloride as an entire molecule. The moles of particle in solution, that would be your sodium ions and your chloride ions. I itself, the Van Hoff factor, is the change in the effective concentration of the ionic compound. Essentially, the Van Hoff factor is used to account for the change in solute concentration caused by the electrolyte breaking up into ions. This will change our colligative property equations. For our boiling point elevation, we can take our original equation and then just multiply the right-hand side by the Van Hoff factor, which gets the variable I. We can do the same thing for freezing point depression and osmotic pressure. The reason for this is if you look at the concentration unit, either molality or molarity in the case of osmotic pressure, the top value, the unit in the numerator, is moles of solute. The purpose of I, our Van Hoff factor, is to scale that moles of solute. Unfortunately, for the vapor pressure, things become a good bit more complicated because the moles of solute in our concentration, the mole fraction, appear both in the numerator and the denominator. So when you are applying the Van Hoff factor to things like vapor pressure, as we will see in the next problem, you need to apply it to both parts of your fraction. You need to apply it wherever you have the moles of solute appearing in your concentration. So for mole fraction, that's both in the numerator and the denominator. Let's look at the Van Hoff factor in effect. Problem 1. Determine the vapor pressure of a solution at 55 degrees Celsius that contains 34.2 grams of sodium chloride in 375 milliliters of water. The vapor pressure of pure water at 55 degrees Celsius is 118.1 torr. The Van Hoff factor for sodium chloride is 1.9, and the density of water at 55 degrees Celsius is 0.9857 grams per milliliter. The equation that we're going to be using for vapor pressure is the vapor pressure of the solvent in the gas phase above a solution, so in this case it's water, is equal to the mole fraction of that component times the vapor pressure of the pure solvent if no solute was added at the same temperature. Now the Van Hoff factor for things like vapor pressure are going to be applied to our concentration. So what we will do is we will take our sodium chloride, our number of moles of sodium chloride, figure that out, multiply that by the Van Hoff factor of 1.9 to give our effective solute concentration. As a reminder, our mole fraction is of component A is equal to the number of moles of A divided by the number of moles total. Because A, this A here, appears both in the top as well as the total. This total would be, we have NA, this would be over component A plus component B plus all your other components. So because the moles can appear both in the top and the bottom, or just in the bottom, if we're looking at our components, we need to apply the Van Hoff factor where it actually works. In this case, because we're interested in water, our water is going to be in the numerator and the denominator. But the Van Hoff factor is not being applied to water, it's being applied to sodium chloride. So what we'll do is we will figure out the number of moles of sodium chloride and then apply the Van Hoff factor to it to scale up to account for it breaking apart into its ions. So we have 34.2 grams of sodium chloride. Take this, multiply it by 1 over the molecular weight, moles on top, grams on bottom, 58.443 grams. Our grams will cancel out. This gives us 0.581856 moles. In terms of significant figures, this value will have 3 significant figures. Okay, so this is the number of formula units of sodium chloride. But sodium chloride breaks up into sodium ions and chloride ions. If we were dealing with an ideal solution, the sodium chloride would break completely apart into sodium ions and chloride ions, in essence doubling the number of solute molecules as compared to the formula units. However, because again some of our sodium ions will be closely associated, will be very close to those chloride ions, they don't all get treated as being separate. Some of them will get treated as being sodium ions, some will be chloride ions, some of them will be together, sodium and chloride combined, and they will be treated as one complete solute molecule. This is why the Van Hoff factor is less than what you would expect from the equation. From the equation of sodium chloride breaking apart, NaCl as a solid breaks up into sodium ions and chloride ions. So what we would expect is our Van Hoff factor, or the amount of ions that we get out of our sodium chloride, to be twice the number of our formula units. But again, because they are closely associated, the Van Hoff factor is going to be some value less than what we would expect under ideal conditions. Under ideal conditions, we would expect 2, but some of the sodium ions and chloride ions remain together. So what this means is that for our number of moles of solute, or our effective concentration of sodium chloride, this would be equal to our Van Hoff factor for our sodium chloride times the number of moles of sodium chloride. So this would be equal to 1.9, this value is given in our problem, times our concentration of sodium chloride that we just worked out, 0.585186. This gives 1.1118, we'll call it 5. Our concentration had 3 sig figs, but the Van Hoff factor here has 2. So our end answer is going to have 2 significant figures. Okay, we also, in order to figure out our mole fraction, need our number of moles of water. Number of moles of water is equal to 375 milliliters times our density, 0.9857 grams over 1 milliliter. Our milliliters cancel out. Multiply this by 1 over our molecular weight. Moles on top, grams on bottom. 1 mole is 18.01528 grams. This will give 20.5180 moles of water. So our mole fraction for water would be equal to the number of moles of water divided by the number of moles of water plus the number of moles of our solute. This will be 20.5180 divided by the sum of 20.5180 plus 1.1118. This would be equal to 0.948598. We can now apply this back to our original equation of the vapor pressure of our water in the gas phase for our solution would be equal to the mole fraction of water times the vapor pressure of the water if it was pure. This is equal to 0.948598 times 118.1 torr, which will give 112.0294 torr. In terms of significant figures, our molarity for our water is good to 3 significant figures. So the top is going to be good to 3. The bottom, when you do it out, will be also good to 3. This value is good to 3 sig figs. And so our end answer will be good to 3 sig figs. Let's look at another problem. For problem 2, the boiling point of an aqueous 1.83 molal ammonium sulfate, which has a molar mass of 132.15 grams per mole, solution is 102.5 degrees Celsius. Determine the value of the Van Hoff factor for the solute if the Kb the boiling point elevation constant for water is 0.512 degrees Celsius per molal. So what this question gets at is this is how one would determine what the Van Hoff factor was from experimental evidence. Our equation is we can take our normal boiling point elevation, the change in our boiling point is equal to the molality times our boiling point elevation constant, and then we just toss in our Van Hoff factor, I, and multiply that by our equation. And this is because molality has the units of moles of our solute divided by the kilograms of solvent. So because the top unit is the moles of the solute, what the Van Hoff factor does is it's essentially a scaling factor for that value. So we can just take our equation here, and what we're after is the Van Hoff factor. So we want to solve for I. So we can just take this equation, divide both sides by m times our Kb, m times our Kb. On the right-hand side, the m, the molalities cancel out, the boiling point elevation constants cancel out, giving us I. So what we get is our Van Hoff factor, I, is equal to the boiling point elevation, how much our boiling point increases by, divided by the molality of our solution times our boiling point elevation constant. We can just plug in our values now. So this is 102.5 degrees Celsius. From this, we subtract the normal boiling point for water, which is 100.0 degrees Celsius, divided by our molality, 1.83 molal, times our boiling point elevation constant, 0.512 degrees Celsius per molal. Our units, the molal cancels out. On the top, degrees Celsius minus degrees Celsius will give us degrees Celsius. So these units here will cancel out that one, giving us our Van Hoff factor as being unitless. If you plug this all into your calculator, what you will find is you get 2.6682. In terms of significant figures, the subtraction up top is going to give you a 2.5. So the top part has two significant figures. The bottom, because it's a multiplication, both the numbers on the bottom have 3 sig figs. So you're looking at 2 sig figs in the numerator, 3 sig figs in the denominator. Your end answer should have 2 significant figures. So this leaves us with an answer of 2.7. Now the chemical equation for the dissolution of our ammonium sulfate would be our ammonium sulfate as a solid, when we put it into solution, will break up into 2 ammonium ions in aqueous solution plus 1 sulfate ion. So just from the balanced equation, what we would predict is that the scaling factor should be 3, but what we find is because some of your ammonium and some of your sulfate are going to be closely associated with each other, the actual Van Hoff factor is slightly less than what would be predicted under ideal circumstances. So our actual Van Hoff factor is 2.7 as opposed to the 3 that would be predicted.